Now, I'm going to skip forward to the next part of this, which is, I'm going to give Michele's talk all over again. That's it, pretty much? No, I've still got further in, right? Yeah, not bad. Yeah, that's exactly it. Okay, I'd like to emphasize in this final session, I'm going to get back to assessment, but particularly talking about inelastic time history analysis, which is clearly the best way to do seismic assessment. I'd like to emphasize that we haven't covered in these presentations a couple of aspects. In particular, we haven't looked at timber structures. I mentioned in the very start of the first session that there is a brief chapter discussing the ductile design of timber structures, pointing out that the displacement-based design is the logical procedure since behavior factor design is largely irrelevant as a consequence of the unusual force displacement response and also of the energy dissipating characteristics. However, if we know that force displacement response, which often has a low initial stiffness and then stiffens up at larger displacements, something difficult to deal with in force-based design, there's no problem in dealing with that in displacement-based design. So there's no conceptual differences. And the brief chapter considers three different types of timber structural systems. Of course, we recognize that timber is not a ductile material. It's very brittle. So any ductility in the structure itself doesn't come from the timber. It comes from the connections between elements itself. So here's one example, perhaps glue laminated beam and column connected by a ring of bolts which go through them to connect them, and those bolts actually they crush the timber on either sides of the bolts itself, creating some inelastic action without fracturing the elements. If we have a structural frame, either of timber or of light gauge steel, then if we have timber shear panels connected to this by nailing, the nails again provide some ductility to the overall response. And typically we can get levels of drift of something like 2% out of this type of design. Another type which has been developed extensively in New Zealand quite recently is the use of pre-stressed timber frames. So we have, essentially it's copying from the precast concrete program in the United States, which looked at precast elements strung together with post-tensioning, unbonded post-tensioning, and with additional energy dissipation in the form of reinforcing bars. Well, what's been done in this timber case is to use glue laminated beams and columns in a prefabricated sense, stringing them together with post-tensioning, and then connecting above and below at the top and the bottom of the beams and the columns, elements which yield in tension and compression as the gaps at each end open and close again. And this has provided extremely attractive behavior and has proved to be an economical structural form for frames up to about 6 stories in New Zealand. Obviously, it depends on the price of timber, but it would be something that I would imagine might be feasible in Costa Rica. Another chapter, as I've mentioned, deals with wharves and piers, where design is dominated by soil structure interaction effects. and which need to be taken into account carefully. Displacement-based design can be used for this to specify limit strains in the piles, which is typically what we do. We design to have inelastic plastic hinges forming at the top of the piles and at depth. Torsional response is critical, and the chapter, which is quite a lengthy chapter in the book, is the basis for the seismic design code of the Port of Los Angeles. So it's using this approach. And the issues associated with this, now we're looking along the length of the wharf itself, is that typically we have the embankment is sloping, and as a consequence we have very short piles here, very long piles here, and these ones here will form plastic hinges at the top and some distance down in the ground, not very far. These ones out here will never form any plastic hinges because they're so flexible. And if I asked you to determine what would be the appropriate ductility capacity for this structure, I don't think you could give me a valid answer. But we can do a pushover analysis of this, having determined where the plastic hinges will form in these structures and at what level of drift, looking at them individually, add them together and get a viable solution for the overall force displacement response, which can be used in a displacement-based environment. And so we talk at both assessment and also of design of such structures, also incorporating torsional effects in this chapter. Now, we've already talked a little bit about analysis tools. I'm going to skip through the first bits of this because it's just emphasizing, it's the chapter where we provide the justification for the fact that yield curvature for a given section is a constant, not the section stiffness itself. We also talk in this in a bit more detail about the capacity, the general philosophy of capacity design. We talk about the concrete strain limits that to use in our designs and the steel strain limits. I've shown all these before, so we can skip through these. And the material design strengths, also we've gone through those. We mentioned that we don't use a strength reduction factor for the flexural design, and we use realistic estimates, not minimum specified strengths, but realistic estimates of the material strengths, because we know that if we've got a ductile design, we expect the strength to be achieved regardless of what we put in. And we've gone through this looking at the difference between current force-based design with its conservative assumptions and the more realistic approach associated with displacement-based. All right, let's look in a bit more detail about analysis tools for design response verification. So this is a little bit different from assessment of existing structures. What we're trying to do here is not to get a rough ballpark idea of what an existing structure is, but to take a structure that we've just designed by displacement-based procedures and do a design verification by a more sophisticated approach. Remembering again that the design procedure, direct displacement-based design, is a very simple process. It's, in our belief, rather robust in terms of the assumptions that it makes, and even though it's a single degree of freedom design approach, we have considered the effects of the higher modes in a much more consistent fashion than has happened. I didn't realize I haven't got this on the... Why didn't someone tell me? Sorry about that. That it's a more consistent approach, but now with in some cases where the structure is more sophisticated or more difficult, we may feel the need to do an analysis using a more sophisticated model to determine what the response really is. In other words, to verify our design. Here we consider a number of possibilities. Time history analysis clearly is one possibility. If we're going to do that, it must be an inelastic time history analysis, not an elastic one. There's no value in doing an elastic time history analysis. Multimodal analysis, this I've indicated many times that I'm not very enamored of multimodal analysis. it has limited application. It's not adequate for determining the displacements, but if based on effective member stiffnesses at maximum response, it can give a good estimate of higher mode effects. Pushover analysis is perhaps the other option to the time history analysis, or often called nonlinear static analysis. Again, limited application. It's not going to tell you what the displacement demand is. All it's going to do is to give you a force displacement response, generally only related to the fundamental inelastic mode. It must be used with an adaptive pushover fashion, which means that you've got to modify the shape of the force vector or displacement vector that you apply as the structure deforms. It's very difficult to incorporate higher mode effects. There are techniques getting developed, but they're even more complex than doing a time history analysis, so there's no real reason why we would want to use it. Well, what level of sophistication do we need to do in element modeling? That's the members. And one of the quotes at the start of the book is Einstein's statement that analysis should be as simple as possible, but no simpler. And we look then, there's the possibility of using line elements, fiber elements, or 3D solid elements. And for the sort of structures that we're talking about, we cross out that bottom line. So we want to look at line elements and fiber elements. And line elements are typically perfectly adequate for frames, also for wall structures and for bridges. They may not be adequate for some other situations. But in looking at this, there are some things that we need to recognize, is that under lateral force, what was going to happen to the structure is we will get compressions, increased compressions in the column over here, and decreased compressions or tensions in the columns over here, and that is going to affect the stiffness and strength of these elements itself. Most time history analyses won't take that into account. They will assume that the elastic stiffness remains constant. Now, if we're going well into the inelastic range, that doesn't matter too much because it won't affect the overall structural response. The same thing happens in terms of the strength. But another aspect then is looking at the joint region and how we model that. And it's important to recognize that the joint is a very flexible region. It's subject to extremely high shear, and as a consequence, there's quite substantial rotations there. A lot of analysts tend to treat the joint as a rigid joint, and this is totally inappropriate. In a typical reinforced concrete building frame or a steel building frame, about 30% of the total deformation comes from joint deformation. So that's pretty significant. You can't throw that out. Now, if you don't have a special joint element which can represent the shear stiffness of the joint, then a reasonable approximation is to say, extend the beam element into the joint centroid with the same stiffness but with unlimited strength. And the same for the columns. Take the column stiffness and extract that with another element into the center of the joint so that this element here has the same stiffness as that but has unlimited strength. It's an elastic element. So that under seismic response, the plastic hinges form at the correct location here and here, but that we get additional deformation due to the joint flexibility. So we would determine the effective stiffness, having designed our structure, based on, this is the elastic stiffness, based on moment curvature analysis of the particular section, so we can determine what its effective moment of inertia is. We note that the variation of member stiffness with axial force is generally not modeled. Shear failure is generally not modeled, but if we're doing a design verification, then we should have made sure that by capacity design approaches, our shear strength exceeded the maximum feasible shear demand, and this should not be a problem. Joint regions and strain penetrations at the base of the structure need careful consideration. Looking at fiber elements, this is a typical column section perhaps, which has a number of reinforcing fibers, and the concrete is subdivided into a series of concrete fibers, and a differentiation is made between the cover fibers and the core fibers. And if we take this into account and have the stress strain characteristics of each concrete fiber and each steel fiber identified, then we can get something which we don't need to do any moment curvature analysis or anything, because that's automatically taken care of in the analysis. And one of the programs in the book, Seismic, is particularly directed towards fiber elements, though it can deal with linear elements as well. Advantages of this is that there is no need to do moment curvature analysis. Hysteretic response is automatically included. The influence of axial force variations on the strength and stiffness is automatically modeled. Biaxial bending is as straightforward as uniaxial bending, and strain softening can be modeled in the response. On the other hand, there are disadvantages as well. It's uncommon for there to be any shear deformation or shear strength incorporation in the model, though that's starting to get now to be incorporated in some of the fiber models. Problems with the plastic hinge length. You know, these, in the out of plane direction here, the fibers have a finite length, and over that, essentially, they have a linear variation in property. And the length that you choose in the region of the plastic hinge very much affects what the deformation capacity will be. So you have to calibrate that by experimental results. Strain penetration needs careful consideration as well. And the computer runtime may be excessive. You know, even for a moderate structure of, say, 7 or 8 stories and 4 bays, if you try and model all of the elements with fibers like that, a single record on a fast PC is likely to take overnight. So it's not very desirable. But we do note that not all members need to be modeled with fiber elements. For example, the columns can be modeled with a linear element, because we know it's not going to get into the inelastic range, or we hope they're not. And also, we perhaps can just use these elements at the ends of beams and have linear elements between the ends of the beams. Mass discretization, well, this is pretty straightforward. We can either have something or other where the mass is distributed to the appropriate distances in the floor plan of a building like this, or we can incorporate torsional mass inertia as with the mass all concentrated at the center. But sometimes people forget about these aspects. For mass discretization of bridges, in most cases it'll be sufficient to concentrate the masses at the top of the piers, as shown here, and these masses will include a certain proportion, typically 1/3 of the pier mass as well. If the spans are long and the superstructure is reasonably flexible, then we may, instead of concentrating the mass at just the top of the columns, distribute it to a number of points along the span, but it will be rare that we would need more than 4 points per span. The same thing applies for the columns. Normally we would not use a distributed mass approximation for the columns unless it's sufficiently high so that we expect that modes of vibration of the columns themselves might be significant. Those are included here. There are situations where we have bearings which mean that the displacement of the superstructure is different from the displacement of the pier, and in this case we need to have the pier mass and the pier and the pier cap mass at this location, the superstructure mass at this location, and a reduced stiffness representing the bearing here and here in relation to this. So pretty straightforward and obvious things, I think. Hysteresis rules. It's important that the hysteresis rules are realistic for the structure being modeled. So we don't want to use an elastoplastic approach for a hysteresis rule for a reinforced concrete element. It's not going to give you the right answer. And also we need to have something appropriate if we're using a hybrid pre-stressed concrete system. So It's just that you need to make sure that the program you're using is capable of modeling the structure properly. There's no point in doing a time history analysis of a structure using the wrong hysteresis rule. Elastic damping in time history analysis, we've already discussed that it's recommended that tangent stiffness be used in elastic damping modeling. This can be a problem in some time history analyses because often you specify the damping by Rayleigh damping, which is a combination of mass proportional and stiffness proportional damping. And no matter what you do in this, in the first mode, the fundamental mode, pretty much all of the damping that you put in, so you specify 5% damping in the first mode, you would typically find, if you then define damping for the third or fourth mode, you'll find that about 80% of the damping in the first mode is associated with mass proportional damping, which is the same as initial stiffness damping. So you're going to get too much elastic damping if that's the case, unless you artificially reduce the damping in the first mode. So you may need to reduce the damping, and there is advice given in the book on how to do this. The next point, just briefly, is to say the representation of seismicity for the design verification. How do we choose the accelerograms? And there are a number of different feelings about that. We can use artificial accelerograms, which are just generated from the design spectrum. We can use recorded accelerograms, which are scaled to fit the design spectrum at critical periods. Or we can use recorded accelerograms, which are manipulated to fit the spectrum over the entire spectrum itself. Now this one here is likely to be the best in that the characteristics of real accelerograms are included, but this one here, scaling recorded accelerograms just by amplitude, is often considered to be the most desirable. But we need to make sure, if we're doing that we know what we're doing. For example, let's say this is the design displacement spectrum, and this is the fundamental period of the structure, the elastic fundamental period, and this is the third mode period, and we make the decision that we want to get the best spectral matching that we can do over that period range. So we do some sort of square root, some of the squares of the errors to get this particular shape here. And we see that that's got pretty good matching over this region. But we've forgotten the fact that what's happening as the structure goes in elastic is that this fundamental period now shifts from here to here. And this is shown, this has been increased by the square root of 3, which is appropriate for a displacement ductility of 3. And you can see that at that level, we've got a very large error in the displacement, in the comparison between the response and this. So really what we need to have is something or other which will match the spectrum, not just over this range, but right up to here at least, if we expect that the ductility demand is 3. So our feeling is that generally it's best to use recorded accelerograms that are manipulated by wavelet theory to match over the entire spectrum range. The disadvantage of that is that it tends to create an artificially long earthquake record. And with an artificially long earthquake record, cumulative damage may be a problem if your computer program models that, which very few of them do. All right, how many earthquake records do we use? And codes have been fairly uniform in doing this. They've said, well, you can use 3 records, but if you use 3 records, you must take the envelope of the response. If you use 7 records or more, then you can take the average response as being indicative of what the performance will be. So a question associated with that would be, okay, I need at least 7 records, but if I generate 14 spectrum compatible records, can I select which 7 I use? And I think that most of you would say, well, no, you can't do that because you're going to take out perhaps the 7 least intense ones or something like that, and that you're manipulating the response. However, it's a trick question, this, and we'll see. because this is what people do all the time without recognizing it. We won't bother about the other 2 points because I'm not going to talk about them just now. So let's look at that business of the response. Here's a little bridge pier which has it's been subjected to 7 different earthquake records. And we look at the maximum positive displacement and the maximum negative displacement. And the green values are the maximum displacements of the two. So for this particular record, this is critical. For this record, this one's critical. This record, this one's critical, and so forth. And these are actual values actually in inches of a wharf structure, not of a bridge structure, but it's easier to explain it in this sense here. So what's the correct average that we should use? Well, what would normally be done is to say, well, we'll take the worst of the positive and the negative displacement. So we take the green values, this plus this plus this plus this plus this plus this plus this divided by 7, which give us a displacement of 7 inches. An alternative approach would be to say, well, I'm going to average all of these, and I'm going to average all of these, and I'm going to average that. So average them all and get 5.8, significantly less. Perhaps it's not greatly significant, but if you're in a pass-fail mentality, if your code says the displacement or the drift has got to be less than 2%, this may be the difference between passing and failing. So what's the critical point? Well, the critical point is that what we're interested in is damage potential, or perhaps if this is a bridge, we might be interested in the maximum displacement at a movement joint, for example. Well, the maximum movement at a movement joint to cause unseating is a displacement in one direction, not displacement in 2 directions. We may also be interested in the concrete compression strain here, whether or not we're going to get crushing. And that's only going to happen under the positive direction of response here. Whereas we might be also interested in the strain in the reinforcing steel, which also is only going to occur in the positive direction of response. So what do we do on this? There are conflicting arguments associated with this. We say that peak displacements in opposite directions should not be averaged if damage potential is considered. For example, plastic hinge compression strain or movement joint opening. But the alternate viewpoint is to say, but the polarity of the earthquake accelerogram is completely arbitrary. We don't know which direction that's going to have. And hence, the displacement signs are arbitrary, and hence the displacements in opposite directions should be averaged. We should take the worst of that. But you can see now why I asked that question before. But what you're doing by this is implying, considering the polarity of both +1 and -1, implying 14 accelerograms, and selecting the 7 most critical. I could just as logically have chosen the 7 least critical with exactly the same justification. But we're not doing it right at the moment. You can see that this is not a valid way of doing it. If you're doing the analysis, you should just consider the average of these values here, or if you like, you can say, yes, I can do 14 accelerograms, but I've got to apply them all to the structure, in which case I come up with this value here of 5.8. In closing this, and before handing over to Michele, the question we ask is, does displacement-based or direct displacement-based design make a difference? Determining moment demand by elastic modal analysis, we've said, is inappropriate, resulting in poor distributions of lateral strength. Force-based design uses elastic stiffness, which is not known at the start of the design. Direct displacement-based design uses yield displacements or drifts, which are known at the start of the design. Displacement-based design achieves a specified limit state at the design intensity. Force-based design at the best is bounded by the limit state, and voltage is variable. The design effort with direct displacement-based design is less than with force-based design. So these are some of the reasons why we should be using displacement-based design. Making a difference? Well, we've already talked about this here, haven't we? In terms of spectral intensity, if we get variations in spectral intensity, force-based results give us a different sensitivity to intensity than displacement-based design does. If we do more rational force-based design involving considerable amounts of iteration, we can improve this behavior, but it's still not going to be the same as displacement-based design. That's a very significant factor. Something as a matter of interest, which I'm not going to bother to go through, but if I compare two buildings which have identical forms except that one's twice as big as the other, the beam sizes, the column sizes, and the masses of each floor are the same for this structure and for this structure, and we do a comparison in terms of the response, we find that the base shear is the same. The base shear is independent of the number of stories. And that's something that is a bit unusual, again, and it's not what you'll get from a force-based design. It doesn't mean that the overturning moment, of course, is different, but the base shears are the same. You can run through this. It's just a dimensional analysis, if you like, of the situation in terms of n, the number of stories, and m, the story mass, and so forth. It's pretty straightforward to calculate. We've already mentioned that in terms of distribution of the strength of a building or a bridge, that displacement-based design does make a difference. We get a different response to this. We distribute the strength in a logical fashion between these piers, whereas force-based design doesn't. We start off with something or other which is in the incorrect sequence of analysis when we do force-based design, starting from stiffness and ending up with rebar. In displacement-based design, we start from the ductility, which we know, and work backwards to determine what the effective stiffnesses are. And the same thing happens with buildings with walls of unequal lengths, where basically the stiffness approach starts in the wrong direction and the displacement-based design goes in the opposite direction and results in differences to the stiffness. The way forward, the final slide, I believe. Displacement-based design obviously needs to be codified so that at least it's an alternative design approach. And there is work going on in this. Alternative design codes have been written for wharves, the Polar Code in the United States, and for bridges, Australia and New Zealand, these are under development. And building structures in general, work particularly done in Italy, but also some additional work going on for building structures in New Zealand. It's likely that displacement-based design will continue to be codified as an acceptable alternative for some years. In other words, we don't expect it to replace force-based design, but to be as a parallel design approach, so you can use either approach. It's also worthwhile noting that displacement-based design can be used at present in most seismic design codes if validated by nonlinear time history analysis. So most codes will say you should design this way, or if you use something or other which is non-standard, you must verify that by nonlinear time history analysis that the drifts aren't exceeded and that the ductility demand of individual members aren't exceeded. And this is how structures have been designed so far. Quite a few designed using nonlinear time history analysis to verify direct displacement-based design. So I think that with that I can say thank you very much. That's the finish of this bit, and we'll hand over to Michele.